Good morning, good afternoon, good evening, depending upon where you're joining us from. I'm Ira Feldman, the tinyML Foundation Managing Director, and welcome to today's webinar as part of our Pedestrian Detection Challenge, where we'll be learning about the Infineon XENSIV 60 gigahertz radar sensor. So welcome, thank you for joining us. And before we go into the presentation, I'd like to thank all our strategic partners who make this and our other programming and events possible. So when you have a moment, please thank them, and I'll tell you more about them at the end of today's presentation. Also, in terms of events, would like to remind everybody that we have the tinyML EMEA Innovation Forum happening the last week of June 26th to 28th. We're very excited. We'll be in Amsterdam. Some important deadlines is the hotel block runs through Monday, May 15th. So if you're joining us and don't have a hotel room yet, please reserve your room. And the discounted registration runs to the end of the month, May 31st. So please register now to save money, and we look forward to seeing everybody in Amsterdam. In terms of resources for the hackathon, we have already had one presentation from Sony on their intelligent vision system. Those materials are up on YouTube and on our website. Today we'll hear from Infineon, and on May 18th, BrainChip will be talking about their platform. We will also have office hours and Ask the Expert sessions as schedules to be announced, and we may have some more dev kits and support resources to announce. So please take advantage of all the resources as you participate in this challenge. In terms of schedule, we have the resource webinars this month. Next week is the optional checkpoint for proposals. And then we have data sets in June, models in July, devices in August, and September 15th is the deadline. So please keep the schedule in mind. And here again is the link for the contest platform, or you can find it linked on the tinyML website under all events. But here is the event contest platform. We're very happy to work with the ITU AI for Good program. And so please check things out there. And today our presenters are Ivan Karan, Application Manager at Infineon Technologies, and Stefan Schoenfeld, Lead Principal System Architect from Infineon. And so I will turn it over to Ivan and Stefan. And with that, I will turn it over to Ivan and Stefan.
Great. Thank you for having us. Welcome from my side. Thank you for joining. Today's session, we want to do a base around XENSIV 60 gigahertz radar sensors from Infineon. And with that, let's go right into the topic. So what do we want to cover today? So many of you might know Infineon. I want to make sure that everybody knows Infineon. So let's start with a general picture and shrink it down to the topic that's of interest today. So we will go through our portfolio and then focus on radar technology, specifically 60 gigahertz radar solutions from our side. Stefan will walk you through our fundamentals and our support tools, from software to tools. At the end, we want to cover a few board items as well as support tools you can use in case you face any issues. And with this, let's start with Infineon. So Infineon has a very broad portfolio. You might know us from automotive or power control systems. That's historically our strongest area. But latest after the acquisition of Cypress, there's a broad variety of other products that are included in the portfolio. So we have connectivity, MCUs, and a variety of sensors in our portfolio. And all of this is supported by our software ecosystem. ModusToolbox is just one of them that I mentioned. You will learn a little bit more about it later. I want to make sure that you understand that we have a variety of solutions. So if we go deeper down into our offerings, you will see that this will help us to create solutions that are dedicated for specific use cases. I want to talk a little bit about our division, so where Stefan and I are located. This division is called PSS, so Power and Sensor Systems, especially the power segment is also focusing on IoT devices. The same thing is applicable for our sensor systems. So we have automotive sensors, we have industrial sensors and consumer sensors. Today, we are going to talk about 60 gigahertz. That's mainly in our industrial and consumer area, focusing on sensor systems in general. Talking about sensors, in our division, we have microphones, 3D radar sensors, environmental sensors. I want to mention CO2 monitoring, as well as 3D time-of-flight image sensors. Today's sessions is based around radar because this is the technology mainly focused for this solution, for the pedestrian monitoring solution. But you can also think about environmental influences with CO2 sensors. Please think about it generically. We have a strong footprint in the industry, so many of our customers are using our sensors. So this will also help you with code examples you will find on our webpage, for example. Let's go further into sensor systems and what we have to offer and what you can use to build your solution. So as mentioned before, radar is the main sensor we are targeting here. So we have the sensors and you will get dev kits for it. Compute element. So there are several tools. You can start with Python, learn a little bit more about technology, get a feeling on the data, and then shrink it down to MCU, tinyML solutions, so machine learning on edge. But we also have connectivity boards. So if you want to test it with Wi-Fi or Bluetooth, because you want to mount it somewhere where you don't want to put your laptop on, you can also do it with our boards. So we combine all of this in especially one board we want to bring to this solution, and we support it with full software stacks. So you will find drivers, tested algorithms, and a lot of tools you can use to leverage our whole potential or your whole potential. Talking about sensors, let's go a little bit deeper, and I don't want to steal too much time from Stefan because he has the interesting part with the technology. But I will cover it broadly. So radar offers a unique proposal. Radar detects motions that's different than the other sensor technologies. This enables very precise localization of any human. It can go through cover materials. That's a big advantage. And it's very flexible. So the same data can be analyzed differently to understand distance, velocity, breathing rates, heart rate. So you can use the same data set to extrapolate different values and get even more out of it. It's very robust. That's one of the unique features I see in this specific use case, because we are not so much limited by sun, time, daytime, nighttime, fog or dust. All of those do not influence our data too much. So that's a big advantage of radar in general. So let's go into the specifics. What can you do with that and the use cases? So I already tackled a few of them, but just to give you a broad idea what we are using it for, those solutions are already in market with several customers. So we use radar to track people. Stefan will show you how it looks like in real data science. But you can actually use this technology to locate a single person and track it while he or she is moving in the room. You can go further. You can use the same technology to also detect if the person is just sitting there. That's a big advantage compared to other technologies. And you can also use it to zone specific areas. This one is a critical area where you don't want people to go. Another area would be a different use case. So it can be used in all of those scenarios. And like I said, it's very flexible in use cases. If you compare us with other technologies, and that's what we try to do here. So just a few advantages in comparison. So I don't want to go to every line, but let's use our biggest competitors in technology side. It's PIR sensors and cameras. So with PIR sensors, you have a very limited design flexibility. So they need to have a output and they need to see a field of view. As mentioned before, you can actually cover a radar. This makes it very nice for for example, waterproof designs. So if you want to have outside or mounted somewhere where it gets wet, it's easier to close the whole design. So you have way more design flexibility with radar compared to PIR. Another big advantage is we are actually detecting presence, and as mentioned before, you can go so far that you actually detect heart and breathing rates or chest movements. So this enables us to stick with the target. So everybody knows the situation in the toilet where you start waving to turn on the light. So this will not happen to you with radar. It's a typical PIR problem. With cameras, let's stay in the toilet. You don't want cameras there. So that's another big advantage of radar. So our data is privacy secure. You cannot see a face. You cannot identify a person. So it has a big privacy advantage. So those are just two that are the main reasons why we see radar as a leading technology and use cases like zoning or presence detection. And for this specific solution, we have a chipset that fits quite well for your needs. So you can use our BGT60, and let's go for the next slide before we go into the technology. So that's the part. We will talk about the boards you need to use in order to get your solutions running. But this part consists of three antennas. So we have one transceiving antenna and three receiving antennas. It uses the FMCW technology, and it can detect not only distance, but as mentioned before, you can use it for zoning. You can use it to distinguish the angle and also the direction. And this is probably a great part to work with in this solution. And with this, I would hand over for the more technical part to Stefan.
Thank you very much, Ivan. Okay, so the question that I'd like to answer first is, I mean, why use millimeter wave radar in the first place for street object detection? Because, I mean, if you look at the in the requirements of the workshop, you will see probably more or 90% of the problem you can solve with vision. Vision models are available. I mean, it's basically just tweaking them a little bit to this application, and then you're done. But I mean, this is probably what everybody will do, and you can reach 90% of the problem. But then is where you can actually make a difference in difficult lighting conditions, like in sunrise, sunset, where the camera is blinded, or in rain or fog where visibility is very limited. So this is where you can make a difference using a radar sensor. Another thing is looking at the judging criteria. There is BOM cost. So if you can replace one camera with a radar sensor, you save a lot of money, because the radar sensor is very, very cheap compared to a good camera. And the other topic is the different weather conditions, where you can really use the radar, even if in no light or in strong fog. I mean, this is probably one of the first applications that radar was used for at all, having sight in fog. Another topic which is not on the list here, but which will be important, is also power consumption. I mean, a camera kit, we learned, will use at least 1 watt for detecting objects and classifying them. With the radar sensors, you can go down to like 10 milliwatt, which is obviously an advantage. I mean, you could think about applications where the cameras are only switched on if the radar is sensing something, and this can bring power consumption significantly down. Okay, obviously having a radar fusion, a sensor fusion between camera and radar will also improve robustness of your solution. And this will bring you there's 1 or 2 additional points that will make the difference between somewhere in the mid-range or in the top of this competition. Good. For those of you who have never worked with radar, I will give a short introduction what radar is about. In the end, we have an RF generator that generates our carrier frequency. This is 60 gigahertz in this case. This goes through an amplifier and is transmitted by the transmitting antenna. It's reflected by the target, received by the receiver, amplified, mixed down to, let's say, A to D convertible frequency. So here we are still in the 60 gigahertz range, and we don't have A to D converters in our microcontrollers that can convert such a range. So, and here we are talking about high kilohertz, low megahertz range, which can be easily sampled by a general purpose MCU. And then basically the rest is software where radar signal processing is applied. The very simplest type of radar is the one most people know from traffic control. It's a Doppler radar, which can sense velocity only, and multiple targets can only be differentiated if they differ in velocity. So basically the transmitter sends out a microwave to the target, and on a moving target, this microwave is shifted in frequency due to the Doppler effect, and the received or the receiver is then receiving a frequency which is a little bit higher than the transmitted one, and again mixing this down will result in a signal depending on the speed of the object. We are using FMCW radar because only FMCW radar can determine velocity and range. So multiple targets can be detected if the targets differ in velocity or range. So for that, we basically generate so-called chirps that are transmitted. So we do not transmit a single frequency, but a ramp, a frequency ramp. So basically a signal where the frequency increases over time. And when this ramp is transmitted to the target and received back, depending on the distance of the target, the signal is shifted in time, and this shift in time results in a frequency change at any point in time, and this again can be detected by can be mixed down and detected by an analog to digital converter. So for the FMCW radar, the frequency or the difference in frequency translates into range, or vice versa. Range translates into a change in frequency. Okay, so let's have a look a little bit into the math that we are doing here. In the end, we have this individual chirps that are basically put into a matrix. And the first thing we do an FFT, fast Fourier transform on the chirps, on the received chirps. And this will lead to a peak for each object in the range dimension. So basically, each FFT bin will each FFT bin represents a range bin. This is how we call it. So if we have a peak there, we know we have an object at 1 meter, 2 meters, 3 meter, depending where this peak is. So, but as these chirps are very close to each other, in the range FFT, they will not look different. So they will basically all have this single object in this single range bin. But then if we look at the phases of these different chirps, we have differences depending on the motion of the object. So if we do a second FFT across every column, we will have the peaks depending on the velocity. So in the end, we will have a matrix with velocity on the one axis and range on the other axis. So if we have, and the further away from the radar an object is, the higher the range bin will be in which the peak is. The same for velocity. Depending on whether the object approaches the sensor or goes away from the sensor, we will create a peak in the positive or the negative velocity range. Okay, so then there is one more thing we can determine from the radar signal, as we have not only one receive antenna, but multiple receive antennas, which have a displacement from one to the other. There will be a small phase shift introduced depending on the angle of arrival from where the signal is basically reflected. So with some simple triangulation, we can determine from the phase difference of these two antennas, we can determine the angle of arrival from where the signal is reflected. And with this, we have not only the range and the velocity of the object, but also the angle of arrival. So we can basically locate the object in a three-dimensional space. So one important thing about radar, or probably one thing that is a bit tricky, is the configuration of the radar, because you have these different chirps, you have amplitudes, you have timings, and all this is important. So I will quickly go through this. So again, we have here these individual chirps of one packet in frequency domain. So we have a start frequency and we have an end frequency, and the difference of these two is the bandwidth. Why is this important? Because the bandwidth determines, together with the speed of light, the range resolution, meaning how many range will be covered by one bin in the range FFT. Then, I mean, we sample these chirps with a number of samples per chirp at a certain sampling rate. And why is this important? Because the number of samples together with the range resolution give you the maximum range the radar will see. So this is important for your applications. You have to know how, is it 15 meters? Is it 10 meters? Is it 20 meters? So then we have multiple of these chirps, which are repeated with a chirp repetition time. And depending on how many chirps we have in one frame, this is then the number of chirps per frame. Why is this important? Because the chirp repetition time will define with together with the wavelength of our center frequency, the maximum velocity that the radar can resolve. And with the number of chirps per frame, this gives the velocity resolution. Let's say how different velocities must be so they are distinguishable in the radar image. Why is this important? Because this is actually determines how good you can distinguish humans from cyclists, for example. We will see that on a later slide. And then finally, there is the frame repetition time. So each frame gives you a measurement at one point in time, and depending on how often you send these frames, the higher the resolution over time is, you can track your target. Good. Let me go a little bit into tooling. So all the one place to go for tooling at Infineon is the Infineon Developer Center. So it's basically a web page and a tool that provides all the different tools that are kind of related to our products. Here I will cover two things. One is the Radar Fusion GUI. This is the first thing I will cover, which is basically a simple GUI where you can configure a radar sensor according to your needs without actually knowing all the math that we looked at before. And then there's the Radar Development Kit, which provides different components which you can use to build your own application on our radar sensors. Here's the link to the Infineon Developer Center, in case you want to look into that right now or after the session. Okay, so let's have a look into the Radar Fusion GUI. So for that, I will bring it up live. So basically, I have one of these boards connected. So I just press this icon and the GUI comes up. Here you can see all these parameters that I just talked about. Chirp repetition time, frame rate, end frequency, start frequency. So now the radar sensor is next to my desk. So if I move my hand in front of the radar sensor, you can see this, whatever happens here happens in the, let me switch on. I cannot switch on the laser pointer, so I need my, so here is this range Doppler image that I just talked about. So you have the range information on the y-axis and the velocity information on the x-axis. So if I move my hand in front of the radar, you will see that basically this hotspot moves from left to right and from right to left at a very small range. So this is because this is configured, the sensor is currently configured to up to 10 meters. So what I can do now, I can increase the bandwidth. So let's make it like this and apply. And then we can see now I reduced the range to 4.5 meters. And now my target is a little bit more out there. So, or I can reduce the chirp repetition time, and then I will have a larger speed range here. Now we have -7 meters per second to 7 meters per second. So now you can see the amplitude of the target is getting smaller. Yeah, and the tool is actually quite nice because it shows you what are the actual limits of the current configuration. So if I change something here, also the limits will get adopted to the new situation. Okay, so this is the nice interactive tool to figure out the initial configuration of your radar, setting up the required range, setting up the required velocity, and figuring out power levels. For example, you can see whether you have clipping or how big your signal is. So this is probably the first thing you will stop by with. So now I go back to the presentation. The next is the radar development kit. This goes a level deeper. So it comes with another introduction to radar, which is probably similar to what I just explained, a little bit more in depth and detail. It comes with the C library for device access and also for the most common algorithms that are used. It comes with application examples for presence detection, segmentation, for radar, raw data acquisition, for recording radar data, and also for constant wave radar. Then there is a Python wrapper. So if you are more familiar with Python, or you like the ease of use of Python, you can use that, and or also MATLAB if this is wanted. Okay, and obviously it comes with all the source code you need to build your application, be it in Python or be it in C or in MATLAB. We also provide a data acquisition kit. So this is one of our eval boards. And this is an Intel RealSense camera, a depth camera, but the data acquisition kit can also be used with any kind of web camera or with the camera of your laptop. This kit is specifically built for data acquisition in ML projects. So we have basically a tool that provides synchronized data acquisition for multiple sensors like radar, RGB, or depth camera. We use open data formats like NumPy or JSON. We have a standard to capture metadata so that everybody can use the same formats for metadata capturing. And we also have tools for automated labeling. So if you have a camera image, you can just use a command line tool to generate these labels and detect objects or detect persons in the field of view of the camera, which will then also be in the field of view of the radar. You can also use these tools to obfuscate the people for privacy protection. All this comes with a Pythonic scripting interface, so it's easy to build your own applications on top of that. Good. So let's have a look how these radar signals look in real life. So I did some recordings in the front of my house. Obviously not one of the most complex scenarios. Let me start this first video. I have to get rid of this. So here you can see me walking in front of the radar sensor. And what you can see here is that I'm getting so this is the range axis, this is the velocity axis. And you can see that the walking person has quite a large spread in the velocity dimension. So basically this is due to the hands and the feet having different velocities while walking. So you can see the range is going probably, a usable range is up to like 17 meters. When I turn around now, you can see me coming back. Okay, let's keep that here. And here's an example for the bicycle. So you can see me here coming from the further away part. And okay, that was wrong. So what you can see here is here in the walking person has quite a large spread in velocity, while the bicycle rider has a rather small spread in velocity. So he has more a spread in the distance. And this is exactly how you can differentiate between the bicyclist and the pedestrian. And this, now it's up to machine learning, do its magic, right? Good. Next slide. Last thing to mention is now we looked mainly into how to model your algorithm, how to prototype your algorithm. Next step will then be to bring this down to an embedded device, because we are talking tinyML. So what we're looking for is bringing it down to an Cortex M0 or Cortex M4 processor. And this is where we introduce ModusToolbox, which is a complete embedded toolchain with GUI, with device configurators, and with this ModusToolbox machine learning extension. You can basically convert your machine learning models directly in this GUI from Keras to C code, to embedded C code, which will run on the microcontroller. You can go through a pre-validation step, check performance, do quantization and pruning, and all these techniques, and then actually put that into the system, build firmware from it, and validate it on the device. And yeah, you can. This is the wrong link, but you can Google for ModusToolbox ML and you will find that. Good, and with that, I'm handing over to Ivan, who will give you an introduction on these boards that we can offer.
Perfect. Thanks a lot. Yes, so there are two boards that are of interest for you. The first one on the left side is the one that Stefan also used for his recordings. It's called the Demo BGT60 TR13C board. This has the advantage that you can stream the data via the USB port and visualize it in the Fusion UI, for example, and use those high data rates to do the machine learning magic, as Stefan described. So for a starting point for you, if you want to start with radar technology and want to learn more about it and learn especially how to use those data sets in your solution, we would recommend you to get this board. We will talk about how to get it in a few minutes. The second one, the KIT CSK BGT60 TR13C, is an embedded solution board. So it comes with a PSoC 6, that's our Cortex M4 MCU. It's a dual core MCU with an M4 and an M0. It has Wi-Fi and Bluetooth capabilities, and it's supported by the ModusToolbox, especially on the machine learning part. And you can deploy your models on our PSoC with the second board. So I would recommend to start with the left one to get a feeling on the technology, see the capabilities, and define your model before going into embedded, and ask for the second one. And with this, let's go for the Infineon community. That's our support structure. So in case you have any questions, feel free to visit this community support page where you can register yourself and ask questions. It's a forum-based, but most importantly, our experts are answering quite fast. So you can actually talk to our CAEs. Those are our engineers supporting all of our products. So feel free to open a thread here and present us your solution. And that's how you also get the board. So please use this forum, enter what you want to do, explain us why you want to use Radar or how you want to use it, and your thoughts on the advantages. And our colleagues will come back to you and let you know if we can ship your board. Once we do that, we will continue all the communication via mail, but please use this thread to start the discussion. Enter your project, tell us what you want to do, also which boards you need, and we will come back to you with instructions how to get the board, how you will get it from our side. And with this, I think we're already at the end. We have some time left, so thank you all for listening. Thank you all for the time. And we continue with questions.
Thank you, Stefan and Ivan. Let's see, so there are some questions, but as I ask them, if other people have questions, do chime in. And I think, Stefan, you talked about the range, but what's sort of the practical limit on detecting a person? I mean, at a certain range, it's just you're probably indistinguishable from other things that move, but is there some practical limits that are?
I mean, looking at the images, you can see that detecting an object should be possible up to 15 meters at least. I mean, this is also about the radar configuration that I talked about. I mean, this is not really tuned. The image of the videos that I showed, they were not really tuned to get farthest range possible. Let me probably go back to that for a second.
Nice. On the video slide where you're about 17 meters.
Here you can basically see a person here at 15 meters. Hard to control. So here at 15 to 17 meters, there's still a clear signal that you can detect. But this border that you see, where you have basically the noise here, and then there is no noise in the background, this is more a theoretical border. It's about the filter that we have implemented into the system, and it can be pushed further out by changing the radar parameters. But in the end, I would think at this range, like up to 15 meters, I would think you have a reasonable signal for the pedestrian. And actually, probably the bicycle rider can be a little bit further out, has a little bit larger radar cross section, like 17 at 5. But where you can really distinguish the two objects would be probably more in the so from 10 meters on, I would say you can really see a difference in the shape of the object.
Right. So the type of
15
object.
meters detection, 10 meters distinguishing or classifying. Yeah. Probably you can get another 20% by tuning radar parameters.
And I'm assuming a car or truck would have a different signature.
Yeah, very much bigger. You will be able to see a truck at 25 meters or something, or a car at 25 meters.
Okay, but it has a different velocity and range signature, so you could differentiate.
It just has also bigger amplitude. So I mean, it will have much more radar cross section and therefore generate a much stronger signal that will stick out of the noise in a very higher distance.
Okay. Cool. And so the toolkits give people tools to, where it finds these, or is this now a signal processing? Somebody or the neural network has to sort of do the signal processing to look at the signature of the signal.
I mean, for the basic signal processing, code is provided. I mean, getting these images, we have code for that.
Right.
Yeah, but I mean, you can do a lot more if you dig into. But I think probably most of the people will just use what we have.
Got it. Okay. Okay. And I think one of the examples, the question was asked, can you detect two or more people and report them separately? And I think that office example where you had the video frames, you were tagging the individual people. So assuming they're not standing right next to each other or in front of each other, there
is a limitation of the TR13, so one transmit, three receive antennas. So you can only detect basically or localize only one object per range bin. So if two persons are walking next to each other at the same range bin, you will not be able to tell that it's really two or whether it's one. So this is a limitation that you have. I mean, if they are not exactly at the same speed or whether they are not exactly at the same angle, and I mean, usually it will be only one frame where they are really at the same location, right? So you can track from frame to frame the individual objects, and in that way, yeah, basically circumvent this problem. Yeah.
Good. Okay. And
I mean, this is not a replacement for vision, at least not in this application. It's an augmentation. It's a measure to get the last 5 to 10%, which cannot be covered by vision.
Okay, got it. Okay. Okay. So the question, well, one last one is, the speed. I think actually they're probably asking about the velocity. What's the max speed detectable from multiple FMCW chirps? And I assume, it just goes back to the math.
Yeah.
So, okay. Okay. This one relates to the noise. Can the noise that's close to the sensor be averaged to get a better signal to noise ratio so detection is more reliable? And would, through your stack, would users have access to the data itself if they wanted to do different signal processing?
Yeah, you will get raw data from the sensor.
Okay, but do you improve the signal to noise ratio by averaging?
Yes, sure.
Okay.
Oh, this is usual signal processing. Yeah.
Okay. And you sort of covered it, but somebody wanted clarity. The pricing for the toolkits shared, those for people who qualify are gratis, correct? Free of charge.
Yes, we have a few boards free of charge. So and we will rank them based on your goals. So please enter your opportunity or your idea to the community, and we will reach out to you and send you a board.
Right. But since the community, they can mark parts of the post private so that they don't give away their competitive entry, right? Correct?
For sure.
Yes. Yeah, okay. Yes. So there's so just use the tools, mark the stuff private that you want private, and then they'll respond. So okay. Another question here. This one's a little off topic because we're not looking at the pedestrian safety, but if you want to address it, or you can defer it to the forum, but could you place, Edward asked, could you place a radar a few centimeters from a person's face and pick up the motion of individual face muscles, such as an eye tracking application for a highly disabled person in a wheelchair? I mean, so this might be a very interesting application. It's not the one we're looking at, but
it's really quite interesting. I mean, radar can penetrate different materials. For example, what we do is material detection. So you can basically distinguish soil from grass and concrete from wood and things like that. right? Because the radar can penetrate the material, and you can analyze this penetration parameters. And I think it will also be able to. Another thing we also do is measuring vital signs like breathing rate and even heart rate on distance. So you can really, the displacement that your heart does on your chest when beating, you can sense this with the radar. I mean, there the signal processing is a little bit more sophisticated, but it can be done. So I would say yes, for sure you can place a radar in front of the face of a person in order to detect differences in how the tension of the muscles is, but you cannot separate different muscles in the face. You could do that with a much higher resolution radar, like much more transmit antennas, much more receiver antennas, but then this will come for a totally different price point.
Okay. Okay.
So this would be imaging radar, basically.
Okay, but actually, this might be an interesting topic for a future challenge. So, Edward, if you're interested in explaining more, reach out to me, and we could consider it for a future challenge. So, but let's go back to pedestrian safety. So, if somebody wants to target a particular area, let's say just the crosswalk, do they do that via, let's say, mechanical shielding of the signal? Or you do sort of sectoring of the data?
No, you can for each target you can determine the position in X, Y, Z, right? So, and if you say X is the width of your corridor, then you can just ignore detections that are out of certain bounds, right? This can be done.
Right. Okay. So you set the bounding box of signals of interest. Okay. Got it. And and you explained, vehicles and things would have different signatures. Does reflections of, let's say, the metal from the vehicles cause confusion, or do they? I mean, will you have like ghost images?
I mean, there's always. I mean, in outside, in larger areas, the problem of multipath distribution is getting smaller. I mean, we have a lot of trouble with that and a lot of challenge with that in indoor scenarios when you are in small rooms, tracking people inside rooms when they walk along the walls. There you have heavy ghost targets that you have to take care of or cancel out somewhere in the algorithm. But if you're in the open space, it's not that bad. No.
Okay, good.
And usually you have the ghost targets very close. If you're walking very close to another object, like as you say a car, but then this ghost target is also very close to the actual target, so your error is not so big.
Cool. I think we've answered all the questions here. You want to bring up the URL for the forum one more time, and for their developer forum. Okay. So this is where people go to get more information, to get request dev kits, ask questions, and I think certainly, as you've highlighted, the radar has certain advantages for the pedestrian safety or pedestrian detection, but people may combine it with vision or try to use it standalone. So it'll be very interesting to see what people come up with. So thank you very much, Ivan and Stefan. That is today's DevKit tutorial. Next week on May 18th at 8 a.m. Pacific, we'll have BrainChip talking about their Kita platform. We will also announce office hours and Ask the Expert sessions. So stay tuned for additional resources. Like all of our content, this recording will be posted to our YouTube channel, youtube.com/tinyml. and also be linked on our website and the contest page. And just a reminder of the schedule, we'd like people to submit proposals for feedback. May 19th, this is an optional checkpoint, as all of them are, but we hope that these will help your development schedules. And remember, the deadline for submissions is September 15th. If you have some general questions or want to share your thoughts with others or look for people to team with, we would recommend you go into the tinyML forum at this URL and ask your questions and discuss with other participants. And if you have general inquiries, please reach out to Rosina. And then I would like to take a few minutes to thank all our sponsors that make this and all our events possible. So our strategic partners are AI Zip, Analog Devices, Arduino, ARM, BrainChip, Edge Impulse, Greenwave Technologies, Gravity, IBM, Imagimob, Initera, Infineon, Microsoft, Noda, NXP, Polyen, Kixo, Qualcomm, Renesas, Schneider, SensiML, Sony, Silicon Labs, ST Microelectronics, Synaptics, and Sentient. And in specific, we would like to thank our executive strategic partners, Edge Impulse, the leading development platform from Edge ML, Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous, Sentient, accelerating your edge compute, making edge AI a reality. Our platinum strategic partners include Renesas, Sony, Atros, and our gold strategic partners, Analog Devices, Arduino, ARM, Infineon, Initera, Microsoft, SensiML, ST Microelectronics, and Synaptics. And our silver strategic partners, we'd like to thank all of them. And we'd like to thank all of you for joining us today. And thank you for participating in this year's tinyML challenge on pedestrian detection. Thank you and have a good rest of your day.